hangis, mga dahon ay magkakahugis. Hindi mo ba na itatanong, mundo'y may ayos na sinusundan, sa math ninyo yan malalaman. Halina, sumama na kayo, maglakbay, mag-enjoy, maglaro, tuklasin ang math sa buhay natin, dali lang mag-math na tayo. Mga number at mga sign, di dapat katakutan, ito'y mga simbolo ng gusto nating sabihin at malaman. Kaya sila'y kaibiganin at kayo'y magtataka, mundo'y mas mauunawaan. Halina, sumama na kayo, maglakbay, mag-enjoy, maglaro, tuklasin ang math sa buhay natin, dali na mag-math na tayo. Halina, sumama na kayo, maglakbay, mag-enjoy, maglaro, analisin, maging matinik.
Hello, I'm Professor Von Schmohawk, and welcome to YU. This series of lectures is an introduction to algebra. But before we discuss algebra, we should start by taking a closer look at the things we call numbers. In even the earliest cultures, understanding and communicating quantities has been essential to everyday life. Anthropologists tell us that even the most primitive Stone Age cultures had some concept of number. However, early number systems were much more limited than today's base 10 number system. Life was simple back then. We didn't need names for exact quantities. If you knew that there were a herd of gazelles nearby, it didn't matter exactly how many gazelles were in the herd or exactly how many miles away they were. What was important was that there were a lot of gazelles and they were just over the hill. Even recently, certain Australian Aboriginal tribes counted only to 2, with any number larger than 2 called much or many. South American Indians along the Amazon had names for numbers up to 6, although 3 were called 21, 4 was 22, and so on. Bushmen of South Africa had a similar way of naming quantities, but stopped at 10 because the names became too long. This tribe would not do financial transactions involving numbers greater than 2. For example, they would not trade 2 cows for 4 pigs. Instead, they would trade 1 cow for 2 pigs, and then in a second transaction, trade another cow for another 2 pigs. If you had never heard of numbers and you want to describe to someone exactly how many gazelles you had seen just over the hill, you might use your fingers to represent how many gazelles there were. Of course, this would become difficult if there were more than 10 gazelles. You could cut marks on a stick or maybe gather a group of pebbles to represent the number of gazelles. But then this would also become cumbersome if there were a lot of gazelles. Another option would be to invent different names and symbols for each possible quantity. This seems like a simple solution, but there is still a problem. Remember that you know nothing about our modern base 10 number system, which uses only 10 symbols in different combinations, so you will have to invent a new word and symbol for every possible quantity. For instance, in my primitive tribe on Coco Loco Island, here are the first 30 numbers we use: Zoop, Bloop, Dop, Trom, Mim, Zap, Weenie, Glumby, Bimpy, Nietzsche, Frump, Wacket, Trimble, Wallachi, Kravitz, Jolo, Ponzo, Kolib, Krub, Wallop, Zumi, Mombozo, Bellimi, Toramu, Balazit, Smip, Bazulu, Ikina, Ichiwa, and After Zortan, we just say a whole bunch. There were several problems with this number system. First of all, since we had over 30 symbols to memorize, math was really difficult. For instance, if you have Wallachi coconuts and then you eat Mim coconuts, how many are left? The answer is obviously Bimpi coconuts, but it takes many years of school to memorize all the combinations. Also, what happens if you have Bazulu coconuts and then someone gives you Trom more? Well, then you'd have a whole bunch of coconuts. In the past, some of the mathematicians on Coco Loco Island actually invented an advanced number system with several thousand names and symbols to handle problems like this. But as soon as they did, someone always came up with a problem which they did not have a number for by adding Zoop to the biggest number. Then, one especially brilliant Cocoloquian mathematician came up with the idea of combining symbols. After Zortan, the next number would be Zortan Zoop, then Zortan Floop, and so on. When you got to Zortan Zortan, you then would go to Zortan Zortan Zoop, and Zortan Zortan Floop. This worked well, but numbers could get quite long. For instance, our number 1000 in Coco Loconian would be Zortan 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 Nietzsche, which we would write as. After many years, people realized that it wasn't necessary to write Zortan over and over. The first symbol could just represent the number of Zortans. For instance, the number Zortan, 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 Zoop would be Dop Zoop. 3 Zortans plus a Zoop. Zortan, 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 Zoop would be Trom Zoop. 4 Zortans plus a Zoop. The first symbol could represent up to Zortan Zortans or 900. This 2-symbol system still couldn't quite get up to 1000, but nobody had that many coconuts anyway. Then one day a boat arrived from the distant island of Bongo Pongo. We were all amazed. The Bongo Ponganians had invented a much better system which could represent really big numbers with much fewer symbols. Apparently, in early prehistory of Bongo Pongo, they must have counted on their fingers because they only used 10 different symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0, which they called fingers or digits. They counted up to Bimpi, which they called 9, using a single digit. After 9, they used 2 digits. The first digit represented some number of tens, and the second digit would add from nothing to 9 to that. For instance, the number 32 would represent 3 tens and 2 ones. The number 47 would be 4 tens and 7 ones. Likewise, the number 80 would be 8 tens and 0 ones. But here is where their number system was really amazing. After getting up to 99, you would think that they would have to stop, but no! They would just tack on another symbol in front, which would now be used to represent hundreds. This could take you all the way to 999, which meant 9 hundreds plus 9 tens plus 9 ones. Every time they got to the biggest number they could represent, they would just tack on another digit, which represented the next bigger number and kept going. This system had some big advantages. First of all, there were only 10 different symbols to remember. Secondly, every time they added a digit, they could represent a number 10 times bigger. So with 6 digits, they could represent almost 1,000,000. That's a lot of coconuts. Looking back, it is easy to see the problem with the first Cocoloquian number system. Each quantity required a new symbol, so when you ran out of symbols, you ran out of numbers. With 30 symbols, the largest quantity that could be represented was 30. The second system allowed these symbols to be combined in a single number and their values added. But since each symbol could add no more than 30 to a number, numbers got big really quick. The third Cocoloquian system could combine 2 symbols, one of which was multiplied by a factor of 30. This allowed larger quantities to be created with only 2 digits. However, the largest number was still less than 1,000. On the other hand, the Bongo-Ponganian system used only 10 symbols. However, with just these 10 symbols, very large quantities could be represented with just a few digits, since each additional digit in a number represented a quantity 10 times bigger than the previous digit. This system was simple and efficient, and the quantities that could be represented were unlimited. That is why this is the number system that the world uses today.
Infinite series is one of the most fascinating subjects in mathematics. But before we talk about infinite series, I would like to ask a question about infinity. What do you get when you add an infinite number of things? A.V. Geekman, do you have an answer up that sleeve of yours?
Well, the more things you add up, the bigger the answer gets. So if you were to add up an infinite number of things, you would always get an infinitely large answer.
Are you sure about that, A.V.?
Well, no matter what size the things are, an infinite number of them will always be infinity. For example, an infinite number of 1s is infinity times 1, or infinity. An infinite number of 1/2s is infinity times 1/2. 1/2 of infinity is still infinity. Even an infinite number of 1/10000000th is 1/10000000th of infinity, which is still infinity.
Aha! That's extremely perceptive of you, A.V. It is true that an infinite number of anything, no matter how small, is still infinitely large. So, another question to you. Is it possible to add an infinite number of things and get a finite number?
Well, based upon our previous discussion, I would say not.
Well then, you would be wrong!
Oh, really?
Now, A.V., as you pointed out, if you add an infinite number of anything, no matter how small, the sum is still infinite. But what if the things you add get progressively smaller?
I don't know.
All right then. Let's add an infinite number of things where each thing is 1/2 of the previous thing. Let's say, for example, that you walk halfway to the wall. Then you walk half of the remaining distance. Then half of that distance, and half of that distance, and so on. No matter how many times you keep doing that, you will still never quite reach the wall.
So it is possible to add up an infinite number of things and get a finite number.
Now you're cooking with gas. I'll give you one more example. Let's take the fraction 9/10, which you can write as the decimal number 0.9. Now, let's add 9 hundredths, and 9 thousandths, and so on. As you can see, we can keep doing this as long as you like, but you will never get a number bigger than 1. We say the limit of this series of additions is 1. So, let's talk about what a series is. A series is just a list of things added together. These things can be numbers, or they can be expressions or formulas which create numbers. Let's call these cute little things that are added together terms. So a series is just a sum of terms. Now, if I wanted you to add a bunch of terms for me, I might write down all of the terms in a list. That list of terms is called a sequence, and when you add all the terms in a sequence together, it is called a series. Now, what if the sequence has a very large number of terms? In fact, what if the sequence is infinite? It might be easier to come up with a formula for creating the terms instead of having to list each one. Now, wouldn't that be a good idea? Wonderful! Now, being the good perceptive professor that you are, you might have noticed there was a pattern to the terms I wrote on your list. If we number the terms 1, 2, 3, etc., then each term is just twice that number. So we can specify this sequence by writing a formula. This formula says that each term, which we will call A, numbered with a little subscript n, which tells us which term in the sequence it is just 2 times n. So for instance, the 20th term, A sub 20, is just 2 times 20, or 40. Now, isn't that easier than listing every term? Of course, we could make the formula for creating terms as complicated as we like, such as, or even something really complicated. But the point is, if we can come up with a formula for creating the terms in the sequence, we can write the sequence in a very compact form and save a lot of paper.
Thank you for showing the class how to write an infinite sequence, Professor Etheline. But weren't you going to explain to the class about infinite series?
Well, thank you, Professor von Schmohawk, for reminding me of that fact. As I mentioned, a series is just the terms of a sequence added together. Now, there is a nice way to write a series using what we mathematicians call summation notation. Here is the summation notation for the first 5 terms in the sequence which I wrote down for the good Professor von Schmohawk. The summation symbol is the capital Greek letter sigma. It indicates that the term to the right is added over and over again, each time using a different value of n. In this case, n starts at 1. This value of n is then used to calculate the first term of the series. Since n is 1, 2n is equal to 2 times 1, or 2. So, 2 is the first term in the series. Then we increase n by 1 and do it again. This calculates the second term of the series. We keep doing this until n finally reaches the value at the top of the summation symbol. So this summation notation is another way of writing these 5 terms added together. The sum of the terms is 30, so this finite series is equal to 30. What if instead of stopping when n equals 5, we went on forever? In this case, instead of the 5 at the top, we would put a little infinity sign. This would then be an infinite series. Now we would keep adding terms forever. In this series, the terms get bigger and bigger, so the sum is obviously infinite. But even if the terms were all the same number, the sum would still be infinite. Take, for example, an infinite series where all the terms are the number 1, or 1/2. In fact, adding any number that's not 0 an infinite number of times gives you infinity. So as long as the terms grow or stay the same, an infinite number of them will always sum up to infinity. But what would happen if each term was smaller than the previous term? Let's take an infinite series of the terms 1 over 2 to the nth power. In this series, the first term is 1 over 2 to the first power, or 1/2. The second term is 1 over 2 squared, or 1/4. The third term is 1 over 2 cubed, or 1/8, and so on. Let's draw a picture of what happens when we add the terms in this series. Start by drawing a square with a length and height of 1, so that the square has an area of 1. Now, the first term of our series is 1/2, so draw a rectangle with an area of half of the square, and place it in the square. Now, the second term of the series is 1/4. Let's draw a square with an area of half of the rectangle, and place it in the square. The third term of our series is 1/8. So let's draw a rectangle with an area of half of the previous square and place it in the square. This process can be repeated forever without overflowing the square. As the little squares and rectangles continue to add up, their total area becomes closer and closer to the area of the big square. The combined area of the terms gets closer and closer to 1. If you could add an infinite number of these terms, the total area would be exactly 1. So we say that this series converges to 1. In other words, this series is convergent. Convergent series are very useful. Some numbers like pi can only be calculated by using convergent infinite series. Here are the first few terms of an infinite series which can be used to calculate pi. Of course, we can't actually add an infinite number of terms unless we had an infinite amount of time. However, we can make our answer as accurate as we like by simply adding enough terms. But will all series converge as long as each term is smaller than the previous one? Well, let's try a series with the terms 1 over n. Now, the first term in this series is 1 divided by 1, or 1. The second term is 1 divided by 2, or 1/2. The third term is 1/3, and so on. Each term is smaller than the previous term. But it turns out that this series does not converge. Even though the terms get smaller and smaller, they will still add up to infinity. We say that this series diverges. Perhaps it seems strange that some series with decreasing terms converge to a number, while other series with decreasing terms diverge to infinity. It is not always obvious which series will converge or diverge. Let's take a closer look at this series to see why it never converges. Let's write down the first few terms of this infinite series. Now, let's make little stacks equal in height to each term in the series. Notice that the first term of the series is equal to 1/2 plus 1/2. The second term in the series is also 1/2. Now notice that the next two terms, 1/3 and 1/4, are each at least as big as 1/4. So, if we add them together, their sum will be at least as big as 1/4 plus 1/4, or 1/2. Now the next four terms, 1/5, 1/6, 1/7, and 1/8, are each at least as big as 1/8. So, if we add them together, their sum will be at least as big as 4 times 1/8, or, once again, 1/2. Likewise, the next 8 terms, 1/9, 1/10, 1/11, 1/12, 1/13, 1/14, 1/15, and 1/16, are each at least as big as 1/16. So, When we add them together, their sum will be bigger than 8 times 1/16, or once again, 1/2. Likewise, the sum of the next 16 terms is bigger than 1/2, and the sum of the next 32 terms is bigger than 1/2, and so on. We can keep going on forever, grouping the terms into sums which equal more than 1/2. So the sum of this infinite series is at least as big as the sum of an infinite number of 1/2s, which is, of course, infinite. This particular series is called a harmonic series because its terms are similar to the harmonics of a musical note. Oh, I diverge. Although the harmonic series is interesting, it is not very useful because its sum never converges. Are there any questions? Hulk Moose Masher, what is your question?
Professor Etheline, are infinite series useful?
Why, yes, Hulk. Infinite series are very useful. There are many things which can only be calculated by using infinite series. For example, the ratio of the circumference of a circle to its diameter is pi. For many centuries, people measured circles but could never determine exactly what this ratio was to an accuracy of more than a few decimal places. But with the help of an infinite series, we can determine pi to any degree of accuracy we like. The more terms in the series we add, the more accurate our answer gets. Infinite series are also used to calculate trigonometric functions such as sine and cosine, which are very useful in determining the angles and lengths of triangles, as well as exponential functions, logarithms, and many other mathematical functions which are used in engineering science and math. I hope this answered your questions. And remember, just like a 90-degree angle, I'm always right!
G'day and welcome to the Tech Math channel. In this video today, what we're going to be having a look at is the fast way of multiplying two-digit numbers together. So let's go. So first of all, we'll see if we can multiply some numbers together. I'll give you a question here, which is 21 times 31. I'll give you 6-7 seconds to work that out. Go. So time's up. Now, if you got the answer as 651, you did really, really well. You got the right answer. If you were busily reaching for the calculator but couldn't find it in time, well, bad luck. You should need a calculator because I'm going to show you how you can work it out that quickly. Okay, so don't get all despondent if you didn't work it out. We'll go through that right now. So I'll show you how to work these out. So to get the first number of our answer, we multiply the first digits in our two numbers here. So 2 times 3 is 6. There you go. We've got the first part of our answer. We leave a blank space, and then to get the last number of our answer, we multiply the last digits of our two numbers here. So 1 times 1 is 1. Alright, now to get this middle number here, there's a bit of a trick with this, and to do this, what we do is we multiply this number and this number, this number and this number, and we add the answer together. So 1 times 2 is 2, 1 times 3 is 3, we add 2 and 3 together, we get the answer 651. Hey, pretty easy, eh? Well, we'll have a look at another one. So, what about 43 times 21? A little bit harder this time. See how you go. Have you got the answer yet? Okay, I'll start working through this one. So again, 4 times 2 is 8. We leave the blank space. 1 times 3, 3. Then what we do is we go, remember this? 1 times 4, we add that to 3 times 2. So 1 times 4 is 4, 3 times 2 is 6. We add these together, and we get the answer of 10. Now this leads to a bit of a problem here, and this is a little bit of a trick that you probably want to get. This space here is only one space. It only has space to fit one digit in. Okay, so the digit that it actually puts in out of this 10 is the 0 here. We put the 0 there, and this 1 here we carry across. Okay, and we add it on. So the answer we end up getting is 1 plus 8 is 903. 903. Oh, good. Hey, I reckon we can go through one more. Okay, so I'll rub that out. let's have a look at one more question. I think this time I'm going to do it in a nice, this sort of purpley sort of colour, and I'll do the question here, 42 times 63. I'm going all out using different colours today, getting excited, go for it. Getting too excited, I can't even wait to get the answer here. Let's just start working it out. So get the first number, 4 times 6 is 24, leave our space. 2 times 3 is 6. And then what we'll do, and I hope I don't do because I had to remake this video because I stuffed up the answer on this one, I'll be honest on this one. Occasionally I get all excited and I do actually make mistakes too, but for YouTube videos we don't make mistakes, we always get it 100% correct, like you guys do, okay? But, okay, we multiply these two guys together. 4 times 3 is 12, 6 times 2 is 12, and so 12 plus 12 is 24. We're going to add 24 on, alright. So there's a 4 there and a 2 there. Alright, what answer did we get? We get the answer of 2,646. Hey, that's the right answer. Pretty cool, right? Okay, so if you practice these, you get really, really good at them, you get really, really fast. Your teacher will be utterly astounded about how great you are. Hey, I know half of you guys probably aren't even going to school, but everyone will be astounded how you guys, people think you're a genius, alright? You don't want to push around too much, people might stop talking to you and that sort of deal because I think you're too smart. But hey, you do this, you'll do really, really well. And yes, you will make a few mistakes. We all make mistakes. So what I'm going to leave you with lastly is I'm going to leave you with a couple of questions. I'll write them up. I'll get you to pause it, work through them, and then I'll work through the answers as quick as I can. Okay, so here they are. So 22 times 34, 32, hey, see how you go on that one. What about 51 times 63? And what about 82, say times 51? So, pause the video, then I'll get back to you in, a couple of seconds and we'll go through these. Alright, so hopefully you've worked through those. We'll work through the answers to these right now, okay? So, 2 times 3 is 6, and we leave that blank space. 2 times 2 is 4, and then we add 4 and 6 together, which is 10. So we're going to get the answer of 704. Okay. There's our answer. The next one, 5 times 6 is 30. Leave a space. 1 times 3 is 3. And then we're going to get the number we're going to put in there is going to be 3 times 5, which is 15. 1 times 6, which is 6. 15 plus 6 is 21. So I'll put that in a different colour so it fits. And that's going to go a 1. And this is going to end up being a 2. So our answer is going to be 3,213. Okay, the very last one. 5 times 8 is 40. Leave a blank space. 1 times 2 is 2. And then what we're going to do is we're going to go 1 times 8 and we're going to add that to 10. 8 plus 10 is 18. So how am I going to put 18 in here? We'll put the 8 there and the 1's going to go there. So our answer is going to be 4,182. I hope you did well on those. I'll see you next time.
Hey guys, what's up? I just want to show you guys a really cool math trick that I learned when I was young. 37. A lot of people think that 37 is a dumb number, it's prime, it's not really divisible by anything except for 1 in itself, but there's really this cool thing about the number 37. Over here we see it divides into 111, 222, all the way down to 999. 37 might be prime, but it divides into all of them. Now, an interesting thing you might notice about these numbers on the right-hand side here is they all have something in common. They're all divisible by 3. And all the numbers here, every single one, is divisible by the number 1. So that leads us over here to these three numbers, 1, 3, and 37. They all divide into 111, all the way down to 999. But interestingly enough, they're all prime. And that's the only number. These are the only numbers that's the case for. 111 divides into all of these numbers as well, but as we see up here, it's not prime. So that's just a really cool thing that I learned about the number 37 when I was younger, and hopefully you think it's cool too.
In a world infatuated with sports stars, crazed by Hollywood tales of good and evil, and obsessed with the possibility that some might possess superhuman powers, who are the real heroes? Youth. Today's youth have the power to make a change that was never before possible, never before conceived, and never before attempted. Our kids can change the world. And my belief is that we can change the world through education one class at a time. I'm Chris Ramey, and my job is to do just that through the power of mathematics. How do you suppose we'll tackle the world through math? What's math got to do with anything? Math is everything, and math is nothing at the same time. It is completely untouchable, but absolutely necessary to explain all things real. We see it in nature, in human behavior, and in works of art and engineering. Math is everywhere. Although a thorough understanding of each and every concept in mathematics is impossible, with a mere fraction of true knowledge, we can make sense of an exponential number of experiences. Math is logic, and math is reasoning. It allows us to hold sensible conversations and to defend our opinions. It reveals our weaknesses and multiplies our strengths. Math is persuasive. Its statistics back our arguments and break down others' false assumptions. Math allows us to argue in favor of far-reaching public causes and against the atrocities of others. Math is preventative. Knowledge of historical trends, both positive and negative, allows us to build a brighter future and sidestep past mistakes.
I wanna be where the talk of the town is about last night when the sun went down. Yeah.
The classroom serves as stomping grounds for the future of our world, and that world had better think for itself. So what better place than the classroom for training our youth to critically think, and for meticulously analyzing our world? Far too often our teenagers use every waking breath trying to get just a taste of something interesting during the school day. Just as often, our teenagers give up in the absence of a meaningful way to relate to what's being taught in their classes. I admit, not all students will become mathematicians, and in fact, very few of them will. However, that does not mean we can't show them how math can benefit creative, artistic, athletic, and other endeavors in life that aren't directly related to math. My goal in the classroom will be to motivate students by showing them how math will be useful to them not only in their future careers, but also in their lives right here and right now. With freedom to choose from a variety of projects and opportunities to explore material in unique ways, my hope is that students will find math in a way that is meaningful to them. When students are able to show off their unique talents in the classroom, it provides an opportunity for them to deepen their creativity and take pride in their work. Of course, my ultimate aspiration is that students will use what they've learned in school to make achievements that far exceed my own and those of others.
You're in control, is there anywhere you wanna go? You're in control, is there anything you wanna know? The future's for discovering. The space in which we travel in.